What if I told you that right now, at this very moment, there's an ocean in our solar system that might be teeming with alien life? And what if I told you we've already tasted it? You're about to visit a moon that changed everything we thought we knew about where life can exist. When you look out at the icy moons of the outer solar system, you're looking at worlds that should be completely frozen. Dead. Inactive for billions of years. Here's the thing. Small worlds far from the sun lose their heat. Fast. Think of it like this. The smaller something is, the faster it cools down. A cup of coffee goes cold quicker than a bathtub of hot water. Do the math on a moon just 500 kilometers across, and you get a world that should have frozen solid billions of years ago. For decades, that's exactly what you thought Enceladus was. A tiny, unremarkable ice ball orbiting Saturn. Just another frozen corpse. You were spectacularly wrong. In 1981, Voyager 2 flew past Saturn's moon system, and you noticed something didn't add up. Enceladus was too bright, absurdly bright, reflecting nearly 100% of the sunlight that hit it. That kind of reflectivity doesn't happen on old, cratered surfaces. It happens when fresh ice is constantly being laid down, which meant geological activity, which meant heat. But where was that heat coming from? The answer: Enceladus isn't orbiting Saturn alone. It's locked in a gravitational dance with a larger moon called Dione. Every time Enceladus completes 2 orbits around Saturn, Dione completes exactly 1. This cosmic rhythm prevents Enceladus from settling into a perfectly circular orbit. Instead, its orbit stays slightly oval-shaped, and that changes everything. As Enceladus swings closer to Saturn and then farther away, Saturn's gravitational pull constantly changes. Stronger when close, weaker when far. This means the moon is literally being squeezed and stretched flexed like a stress ball in the hand of a gas giant. That flexing generates friction. Friction generates heat. And heat in the outer solar system is everything. This is the same force that powers the volcanic hellscape of Jupiter's moon, Io, and probably keeps oceans liquid beneath the ice on Europa and Ganymede. But Enceladus takes this to another level. Because unlike those other worlds, Enceladus doesn't keep its secrets. Fast forward to 2005. You're on the Cassini spacecraft beginning detailed reconnaissance of Saturn's moons, and when you turn your cameras to Enceladus, you see something that shouldn't exist. Near the South Pole, 4 parallel cracks cutting across the ice, each about 130 kilometers long. The team nicknamed them tiger stripes, but here's where it gets wild. These fractures were warm. Not by a little, we're talking about 200 degrees warmer than the surrounding terrain. In a place that should be around minus 200 degrees Celsius, these stripes were nearly 100 degrees warmer. And then you saw them, massive plumes of ice and vapor erupting from these fractures, shooting hundreds of kilometers into space. Enceladus wasn't just geologically active. It was actively spraying its interior into orbit around Saturn. This is where your mission became something extraordinary. You didn't just observe these plumes, you flew through them. Multiple times. And each pass was like taking a sample directly from Enceladus's subsurface ocean. Your instruments detected water vapor. Lots of it. But also salts. The kind you get when liquid water has been touching rock for a long, long time. This wasn't melted surface ice. This was ocean water. Then came the organic molecules, carbon-based chemistry. The building blocks of life. Then molecular hydrogen. That last one is critical. Let me tell you why. On Earth, some of our most ancient ecosystems exist in complete darkness at the bottom of the ocean, clustered around hydrothermal vents. No sunlight. They run on chemical energy instead. When you detected molecular hydrogen in Enceladus's plumes, you detected the signature of a chemical reaction that happens when water meets certain rocks at high temperatures. This reaction produces hydrogen gas and releases energy. And here's the key. Molecular hydrogen is high-energy fuel. Life can use it. In fact, on Earth, the amount of hydrogen coming out of Enceladus's ocean would be enough to support a substantial microbial ecosystem. This isn't speculation about whether liquid water exists. This is chemistry that's actively producing food for life, right now. Let's step back and think about what life actually needs to exist. You need 3 things. 1. A liquid. Water works great because it can dissolve all kinds of stuff and stay liquid across a wide range of temperatures. 2. Energy. Doesn't have to be sunlight. Any energy source will do. On Enceladus, that's chemical energy from underwater vents. 3. The right chemistry. Carbon-based organic molecules, the building blocks for complex chemistry. Enceladus has those in abundance. Check, check, and check. But here's where it gets philosophically interesting. You have a problem. Everything you know about biology comes from one example: Earth. So when you ask, could life exist on Enceladus, you're really asking, could Earth-like life exist on Enceladus? And the answer appears to be quite possibly yes. But what if you're thinking too small? Life on Earth emerged relatively quickly after the planet became habitable, within a few 100 million years. This suggests that the origin of life might not be that rare, given the right conditions. If true, then Enceladus's ocean stable for potentially billions of years has had plenty of time for life to emerge. But would that life resemble anything you'd recognize? Imagine you're a microbe in Enceladus's ocean. You've never experienced day or night, because no sunlight has penetrated to your world in 4 billion years. You don't know what a season is. You have no concept of up, except as a direction where things get colder and the pressure gets heavier. Your entire universe is defined by temperature differences near underwater vents, chemical gradients where mineral-rich water meets the wider ocean, and pressure differences in the water. If you evolved sensory organs, they wouldn't be eyes. Maybe chemical sensors to detect food molecules. Maybe sensors to feel water currents. Maybe organs sensitive to heat. You would be shaped entirely by an environment nothing like the one that shaped life on Earth, and yet, at the molecular level, you might be using the same basic tricks: proteins for structure and speeding up reactions, DNA and RNA for storing information, lipid membranes to keep everything contained. Because those solutions work, and evolution finds what works. Here's the uncomfortable question you need to ask: should you go looking? Right now, you can sample Enceladus's plumes from orbit. You can fly through them, collect ice grains, analyze them, and never touch the surface. It's the most accessible ocean in the solar system for study. But if you want to really know, if you want to send a probe down through the ice into that dark ocean, you face a problem. Earth microbes are tough. Some can survive years in the vacuum of space. Some can handle extreme radiation. Some can stay dormant for thousands of years and wake up when conditions improve. And every spacecraft you've ever sent into space, despite your best sterilization efforts, has carried Earth microbes with it. If you crack through Enceladus's ice and send a probe into that ocean, can you guarantee you won't contaminate the most pristine biosphere you've ever discovered? This is called forward contamination, and it's covered by the Outer Space Treaty and International Planetary Protection Guidelines. But those guidelines were written before you knew Enceladus had an ocean. Because here's the thing: if you contaminate Enceladus with Earth life, you might never know if you discovered alien biology or just your own microbes thriving in a new environment. Let's say you find life on Enceladus. Definitively. Unambiguously. What would that mean? Well, it would answer a huge question. How often does life actually start on habitable worlds? If life arose independently on 2 different worlds in the same solar system, that suggests life isn't rare. It's not a cosmic fluke. Which means the universe is probably full of life. Most of it will be microbial. Most of it will never evolve intelligence. Most of it will never know you exist, and you'll never know it exists, but it means you're not alone. You never were. And it means the story of biology isn't just Earth's story. It's woven into the fabric of the universe itself, emerging wherever the physics allows it, in the darkness beneath ice, in the depths of subsurface oceans, in places you haven't even thought to look yet. So where do you go from here? NASA and ESA are planning missions, orbiters to better analyze the plumes, landers that could study the tiger stripes up close, eventually maybe thermal probes that could melt through the ice and drop submersibles into the ocean itself. But those missions are decades away. For now, you're left with Cassini's data, with the tantalizing possibility that you've already detected the chemical signatures of alien life and just haven't confirmed it yet. You have one example of life Earth and a growing list of places that might harbor life. Enceladus is at the top of that list. Enceladus is a 500-kilometer wide moon orbiting Saturn, 1.4 billion kilometers from Earth. Beneath 20 to 30 kilometers of ice lies an ocean, kept liquid by gravitational squeezing, enriched with minerals from underwater vents, full of organic chemistry and fuel for life. It is, by every measure you have, a habitable environment. Whether it's actually inhabited is the next question. And answering that question might change everything. Because if life emerged independently on a small, dark moon in the outer solar system, if it found a way to exist in conditions nothing like Earth's, then life isn't special. It's just what matter does, given enough time and the right conditions. And you're living in a universe where those conditions exist everywhere. Space-time.